Some numbers seem to work perfectly in the Pythagorean theorem, like 3, 4, and 5. Sets of positive whole numbers that work in the Pythagorean theorem are called Pythagorean triples. This video lesson will teach you to identify a Pythagorean triple, apply the Pythagorean theorem, categorize a Pythagorean triple as either primitive or imprimitive, not primitive, and use the Pythagorean theorem and another method to find Pythagorean triples. Let's start. What are Pythagorean triples? For three positive integers to be Pythagorean triples, they must work in the Pythagorean theorem's formula. A squared plus b squared equals c squared. In the Pythagorean theorem's formula, A and B are legs of a right triangle, and C is the hypotenuse. Only positive integers can be Pythagorean triples. The smallest Pythagorean triple is our example, 3, 4, and 5. A quick way to find many more triples is to multiply all the original terms by another positive integer. For example, take 3, 4, and 5 and multiply by 2 to get 6, 8, 10. Multiply by 3 to get 9, 12, 15. Multiply by 4 to get 12, 16, 20. And multiply by 5 to get 15, 20, 25. You can categorize a Pythagorean triple as either primitive or imprimitive, which means not primitive. A set of numbers is considered to be a primitive Pythagorean triple if the three numbers have no common divisor other than 1. The Pythagorean triples are relatively prime. Relatively prime means they have no common divisor other than 1, even if the numbers are not prime numbers like 14 and 15. The number 14 has factors 1, 2, 7, and 14. The number 15 has factors 1, 3, 5, and 15. Their only common factor is 1. Our first Pythagorean triple is primitive, since 3, 4, and 5 have no common divisors other than 1. Our fifth set from our example above, however, is not primitive. It is imprimitive, because each value for A, B, and C of the right triangle is a multiple of 5. Keep in mind, primitive Pythagorean triples will always have one even number. The value for C will always be odd. Many primitive Pythagorean triples have two prime numbers. You can use that information to find primitive Pythagorean triples. Pick an even number to be the longer leg's length. Find a prime number, one greater than that even number, to be the hypotenuse. Calculate the third value. Suppose you pick 12 as the length of a leg, knowing 13 is an adjacent prime number. Use these two as part of the Pythagorean theorem. Let's start with our formula. A squared plus b squared equals c squared. Then we plug in the length of the longer leg and the hypotenuse like this. A squared plus 12 squared equals 13 squared. Then we multiply each number times itself and get a squared plus 144 equals 169. Subtract the value of b squared from both sides and we get a squared equals 25. Now, we take the square root of both sides and get our answer, a equals 5. So our primitive Pythagorean triple is 5, 12, 13. You can quickly generate iterations of that, none of which will be primitive, using the same multiplying method we used before. Times it by 2 to get 10, 24, 26. Times it by 3 to get 15, 36, 39, and so on. All the right triangles made using these multiples of our original primitive Pythagorean triple will be similar as well. Let's dive into another example. Generate a primitive Pythagorean triple based on the prime number 41. What even number is adjacent to and smaller than 41? 40. Let's plug this into our formula and solve for a. A squared plus 40 squared equals 41 squared. Then we multiply each number times itself and subtract the value of b squared from both sides. We get a squared equals 81. Then we take the square root of both sides and get our answer. Did you get a equals 9? The primitive Pythagorean triple is 9, 40, 41. You can come up with your own Pythagorean triples. Label two positive integers, m and n, ensuring m is greater than n. Then for each side of a right triangle, a equals m squared minus n squared, b equals 2 times n times m, and c equals n squared plus m squared. Let's try it. Generate a set of Pythagorean triples for m equals 6 and n equals 5. First, let's solve for a. Plug into our formula and we get a equals 6 squared minus 5 squared. Then we multiply each number times itself, subtract, and get a equals 11. Now, let's solve for b. Plug into our formula and get b equals 2 times 5 times 6. Multiply to get b equals 60. And finally, c. Plug into our formula and get c equals 5 squared plus 6 squared. Then we multiply each number times itself, add, and get c equals 61. Our Pythagorean triple is 11, 60, 61. This method catches both primitive and imprimitive Pythagorean triples. Lesson summary. You have learned how to identify a Pythagorean triple, apply and use the Pythagorean theorem, classify a Pythagorean triple as either primitive or imprimitive, and use both the Pythagorean theorem and another method to find Pythagorean triples.